Students, can you see the board? Yes. Okay, very good. So, last day I have discussed that the concept, that is what is the dissociation of water and what is the relation between the dissociation of an weak acid in its aqueous solution. In this way, we have defined a lots of term regarding to the equilibrium, what is buffer solution, what is buffer capacity, and what is the sparingly soluble salt and the solubility product. These having the concept only the sparingly soluble salt, that is KSP or solubility product was running, but today I will start from the concept of dissociation of H2O. Dissociation of H2O. I have done it on the earlier class, that is how water is dissociates. Okay. So, H2O is a weak electrolyte. So, H2O dissociates as one of its molecule will act as an acid, that is it will release the proton, and another molecule which takes up this proton forming H3O plus and A minus, right. Now, for this reaction we can express it by using the dissociation constant or equilibrium equation. It is the concentration of H3O plus, concentration of A minus by concentration of H2O square. Now, concentration of H2O, that is equal to 1, that is K equal to concentration of H3O plus into concentration of A minus. It is represented as Kw, it is represented as Kw, that is concentration of H3O plus and concentration of A minus, right. Sorry, here it will be OH minus. So, here it will be OH minus, here OH minus. In this way, so it is equal to Kw. At 25 degree centigrade, that is, as the dissociation is a temperature dependent parameter, at 25 degree centigrade Kw having the value of 10 to the power minus 14. Now, the concentration of these two species in the solutions are equal, which is proved by the equilibrium equation, that it is the both the components concentration is equal. So, if it is assuming that the concentration is equal H3O plus, that is 10 to the power minus 14. So, concentration of H3O plus square, because the concentration is same. So, according to mathematical term we can tell it is equal to 10 to the power minus 14, that is concentration of H3O plus, that is equal to 10 to the power minus 7. On the reverse way, the concentration of OH minus, it is also 10 to the power minus 7. Clear? Concentration of OH minus equal to 10 to the power minus 7. Next step is, what is pH? What is pH? Now, we know the basic definition of pH. It is the representation of the hydrogen ion potential in the solution. In mathematical term, there is a representation for pH. It is equal to minus log, that is logarithm 10 concentration of H plus, right. It is the minus log 10 concentration of H plus. So, concentration of H3O plus into concentration of OH minus, that is equal to 10 to the power minus 14. Now, how log function works we have to know, because the mathematical problem will come from here, that is the deduction of calculation of pH or the calculation of the dissociation constant. Here maybe we have to use the logarithmic function. So, pH equal to minus logarithm of H plus. We wants to relate the pH and POH. What is POH? In the reverse way, it is POH equal to, that is POH equal to minus logarithm of concentration of OH minus. Now, H3O plus, here the rules is if log xy is equal to log x plus log y, log xy equal to log x plus log y, clear. Next, log x to the power y, that is equal to y log x, log x to the power y equal to y log x. So, the power comes before the function with its sign. Here we will apply the first rule, that is xy, that is logarithm of this xy, that is equal to log x, log of concentration of H3O plus log of concentration of OH minus, that is equal to logarithm of 10 to the power minus 14, 10 to the power minus 14. So, if we want to convert it to pH, then what will happen? If we convert it to pH, then what will happen? Taking a minus sign, that minus logarithm concentration of H3O plus minus logarithm of OH minus, that is minus log 10 to the power minus 14. Here we will apply log x to the power y. Here it is equal to pH plus POH, that is equal to minus minus plus, that is 14 log 10. So, it is equal to 14 because log 10 is equal to 1, log 10 equal to 1. You have to remember the data of log 1, log 2, log 3, log 5 and log 7. These 5 data you have to remember for the calculation, because we can simplify all the equation to this form. Okay. So, log 1 having 2, log 2 having 0.30, log 3 having 0.447 or 48 in this way. Okay. So, pH equal to plus POH equal to 14. So, pH equal to 14 minus POH, in the reverse way POH equal to 14 minus pH. Clear? Clear, students? Now, next step, it will be the dissociation of a weak acid and its conjugate base. Dissociation of an weak acid and its conjugate base. So, the topic is dissociation of an weak acid and its conjugate base. Now, first of all, dissociation of an weak acid. Ha plus H2O forming H3O plus A minus. It is the dissociation of an weak acid, that is Ha. It is the equation 1. Next one, A minus, that is the working of base, that is the conjugate base, plus H2O forming Ha plus OH minus. Right? Clear? From first equation, it is Ka because it is the acid, Arrhenius acid. So, Ka equal to concentration of H3O plus into concentration of A minus by concentration of Ha into concentration of H2O. Clear? Now, concentration of H2O is equal to 1 because it is a pure solvent. So, the concentration of H2O is 1. Hence, Ka equal to concentration of H3O plus concentration of A minus by concentration of Ha. Okay. From the second equation, Kb, that is equal to concentration of Ha, concentration of OH minus divided by concentration of A minus into concentration of H2O. Here also same rule, that is concentration of H2O equal to 1. So, it will be equal to concentration of Ha, concentration of OH minus by concentration of A minus. Right. Now, I will rub the upper portion, that is, if we want to calculate the relation between Ka and Kb, just multiply these two, that is Ka into Kb, then you can find that after simplifying, the residue part will be H3O plus into concentration of OH minus. It will be further transferred to Kw because it is the water dissociation, the dissociation of water. So, Ka into Kb, that is the dissociation constant of acid and dissociation constant of conjugate base, is equal to a constant value, that is equal to Kw, right, because Kw having a fixed value at a fixed temperature at 25 degree centigrade, it is equal to 10 to the power minus 14. Okay. Now, next stage, there we know pH. Now, on the basis of this, we may solve out some problem regarding to the pH, that is, write it down everyone. Find the pH of a solution, find the pH of a solution of, find the pH of a solution of 0.01 molar acetic acid, find the pH of a solution of 0.01 molar acetic acid which is only 20% ionized, which is only 20% ionized. Find the pH of a solution of acetic acid having the molar concentration 0.01 m and which is 20% ionized. Now, from the dissociation equation, we can calculate the concentration of the H3O plus. So, first of all, writing down the dissociation equation, CH3COOH plus H2O forming H3O plus and CH3COO minus. This is the value of pH. If we want, if you have the value of concentration of H3O plus, then we will easily calculate the value of pH. Concentration of CH3COOH will be C into alpha, the C equal to 0.01. Now, alpha equal to 20%, that is 20 by 100, that is equal to 0.002, right. It will be the concentration of H3O plus. Now, next stage we have to calculate pH equal to minus logarithm concentration of H3O plus, that is minus log of 0.002. Now, here we have to simplify this, just 0.002 we may write it, we may write it is equal to 2 into 10 to the power minus 3, because 2 divided by 1,000, that is equal to 0.002. Okay. Next, it will be assumed as xy, that is log xy. Now, we will use the simple rules, that is log x plus log y, and in the next step it will come the log x to the power y. The first step is log xy, x into y, that is log x plus log y, and in the second step, so just log 2 minus log 10 to the power minus 3, here x to the power y works minus log 2, log 2 having value of 0.3, minus plus 3 log 10, that is equal to 3 minus 0.3, that is equal to 2.7. So, the pH of the solution is 2.7, right. Any problem? Just match the statement, that is find the pH of a solution of 0.01 molar acetic acid which is only 20% ionized. Find the constant pH of the solution of an acetic acid 0.01 molar acetic acid which is 20% ionized, right. Another one problem we may solve regarding the pH. Here an weak electrolyte, that is acetic acid, is used. Now, if it is the case of a strong electrolyte, then it is the next problem. Calculate the pH value of 0.2 molar H2SO4 solution. Find the pH of 0.2 molar H2SO4 solution and 0.2 molar calcium hydroxide solution. So, first case, find the pH of, find the pH of 0.2 molar H2SO4 solution. Find the pH of 0.2 molar H2SO4 solution. Okay. So, first of all we know the dissociation constant, that is H2SO4 is dissociated as 2H plus SO4 2 minus. Here alpha does not work because it is a strong electrolyte. So, the concentration of H plus is 2 into 0.2, that is equal to 0.4 molar, because the numerical coefficient is 2 here, here 1. So, the concentration of which was 0.2, it will be multiplied by 2. Now, pH equal to minus log concentration of H plus, that is minus logarithm of 0.4 log 0.4, that is equal to 4 into 10 to the power minus 1, that is minus log 4 minus log of 10 to the power minus 1. So, it will be equal to 1 and log 4 equal to minus log of 2 square minus plus 1 because log 10 equal to 1, log 10 equal to 1. Next step I am writing down here, that is equal to minus 2 log 2 plus 1, 2 log 2 plus 1. Why 2 into 0.2? Okay, 2 into 0.2 because the concentration of acid was 1 molar. From 1 molar H2SO4, from 1 molecule of H2SO4, 2 molecules or 2 mole of H2SO4 produces. From 1 mole of H2SO4, 2 moles of H plus produces. It is proved by the numeric, that is the numerical coefficient, that is here 2H plus. So, as 2 hydrogen atom is here, it will be multiplied by 2. Just to the concentration of H plus is multiplied by 2 for the numerical coefficient. Zero point two is given. 0.2 is given. The problem tells that calculate the pH value of 0.2 molar H2SO4. It is given in the statement. Okay. Now, it is equal to the last form, it is equal to 10 into 10 to the power minus 4, or from the direct value, that is 0.4 having the value of 0.3979. You can simplify in this way, that is 2 log 2, that is 2 log 2, that means 2 into 0.3, that is 6, 0.6 plus 1, it will be minus 2 log 2 plus 1. So, 2 log 2 equal to 2 into 0.3 plus 1. I am writing it here. It is equal to minus 0.6 plus 1. So, 0.3, roughly it is 0.3. So, the pH of the solution is 0.3. Clear? Now, write it down. In the same way, there was another part of this question that the calculate the pH of 0.2 molar calcium hydroxide solution. Clear, students? How to calculate the pH? So, when we have used the weak electrolytes, then the dissociation was different. But for strong electrolytes, the dissociation was different and there is the term used. But if it was HCl, in place of H2SO4 it was HCl, then it will only be 0.2, not multiplied by 2. It will be only 0.2 if it will be HCl. Clear? So, next problem, that is find the pH of 0.2 molar calcium hydroxide. Now, calcium hydroxide will produce Ca2 plus and OH minus, right? Calcium hydroxide will produce Ca2 plus and OH minus, that is 2 OH minus. So, first of all we know pH plus pOH equal to 14. So, we will calculate the pOH first and then it will be subtract from 14. Just see that. So, first of all CaOH whole twice that is equal to Ca2 plus 2OH minus. Just the concept from the previous one, that is here the concentration of OH minus will be doubled, that is 2OH minus. So, 2 into 0.2, that is equal to 0.4. Now, from here POH equal to minus logarithm of 0.4, the value is known to us, that is equal to 0.36 etc. So, pH will be equal to 14 minus POH, that is equal to 14 minus 0.36, that is equal to 13.64. 13.64. It will be the pH of the medium, that is pH of the calcium hydroxide solution. Now, tell me, is this clear? These three problems are from different areas, that is one for weak acid, another one for strong acid, and last one was for a strong base. Very good. Have you written this problem? Okay. So, I am rubbing this portion. Now, moving to the next. Next is the theoretical part is there. The theoretical part is that what is buffer solution? What is buffer solution? Now, when a solution restricts the change in pH, when a buffer solution a buffer solution is that buffer solution. A buffer solution is that which restricts the change in pH in the medium, which restricts the change in pH of the medium is known as buffer solution. Now, buffer solution may be of two types. One is acidic buffer and basic buffer. Basic buffer. Now, weak acid, which can work as acidic buffer, that is weak acid and its salt, weak acid and its salt, and basic buffer is weak base and its salt. Okay. So, acidic buffer, that is weak acid and its salt, and basic buffer, that is weak base and its salt. One example of weak acid, that is acetic acid, and its salt, that is sodium acetate. Weak base NH4OH and its salt, that is NH4Cl. Okay. So, in this way we can define the buffer solution. Next is what is buffer capacity? Buffer capacity. Okay. So, what is buffer capacity? That is the to which extent one buffer solution can restrict the change in pH, that is the strength of the solution as a buffer. The strength of the solution as a buffer is called its buffer capacity. Strength of the solution as buffer is called its buffer capacity, right. In this way, next session is that how the solution restricts the change in pH. For an example, suppose acetic acid and sodium acetate is taken. Okay, I am writing down NH4OH weakly dissociates to produce NH4 plus and OH minus, and NH4Cl, as it is a base or as it is a salt of weak base, it is strong in nature, it will produce NH4 plus and Cl minus. For this reason I have written their arrow, that is only the forward arrow. Now, in a buffer solution there is the presence of NH4 plus Cl minus OH minus NH4 plus. Now if we add H plus here, H plus, so it will interact with the OH minus producing H2O, and which H2O is a weak electrolyte and its pH is also neutral. So, the pH of the solution will be the same, that is it restricts the pH to that level. If we add OH minus, then the concentration of OH minus in the right side will be higher. So, from the last atelier concept or last atelier principle, as the concentration of OH minus is higher in the product side, the reaction, that is the first one reaction, will move to the reverse direction, that is the NH4OH will be produced. So, as NH4OH is a weak electrolyte, so the pH maintained at constant. In this way, the buffer restricts the small change in pH. Okay. Now, the Anderson equation and this portion are left out from your syllabus. Next day I will discuss on the what is solubility and solubility product. What is solubility and solubility product? Is this clear, student? Up to this we have discussed about the buffer solution. Is it clear to everyone? Okay, thank you very much and bye bye. Wait for the next class, it will be the English with Partho sir. Okay.